First off, I'm going to have an admission here. I'm going to speed through this because there's a lot to unpack and I talk a lot. I can dig into any of these things. If you have a question that is material to what I'm talking about, like I didn't explain it well or you didn't understand it, which is the same thing, please interrupt me anytime. If you want to sidetrack, if you want to talk implementations or how you could use this in your everyday work, please see me afterwards because we're probably going to be 49 minutes and 60 seconds. All right? So, my name is Daniel. I'm talking about cryptography, and cryptography is such a huge field. It is very nerdy, but it's such an immensely huge field. And up until the 70s, much of its research was even just not publicly available because it was probably just military applications. I'm covering this little box up there, right? So we're going to talk about basics today. If you have a basic understanding of math and none of cryptography, this session is for you. So my name is Daniel. I'm a SQL Server developer, general nerd. Microsoft found fit to make me an MVP. I run conferences. I run a couple of websites. I'll show you the contact information after the session. This is probably the most basic substitution encryption that you may have heard of. It's the Caesar shift. Basically, some genius 2,000 years ago discovered that if you just shift all of the letters in the alphabet to one or the other direction, it is completely unreadable to anyone else. Perfectly secret. No one will figure this out. And to decrypt it, you just shift it back one character, right? Don't use this. Substitution encryptions are when you switch out certain characters according to a certain key. So you have basically an alphabet and you have a scrambled alphabet. So everyone, the key is basically how to switch out those characters, right? Is this good, strong encryption? No? How would you crack it? So every language has a frequency in which every character appears. If the text is large enough, in English, for instance, 12.7% in a large enough corpus of text will be the character E. 8.2% of all characters will be the character A, and you don't need to be able to read that. You get the general gist. So what you do is you put your ciphertext like on the screen, you measure the frequency at which every character occurs, which generates the table on the left. Then you sort this. So you see you have V, G, L, Z, R, which would probably, if this is a large enough corpus of text, would correspond the English characters E, T, A, O, I, and so on. Now we start substituting those characters, and we see what we get, right? But it's not perfect because a large text will never be, yeah, some of you get it. A large enough text will never be perfectly distributed. So we will have to do individual substitutions just to get the text right and readable. When do you think someone figured this stuff out? Almost 2,000 years ago. It was, I'm doing the math now, 1,600 years ago. In ancient Arabia, there were like multi-scientist type persons, kind of like the scientists of the Renaissance, Da Vinci. They were not just mathematicians, they were legal scholars, they were doctors, they were astronomers, whatever. And there was a guy whose name I don't remember, I'm sorry, who figured out how to do frequency analysis in the 800s, so it's 1,200 years ago. So this stuff was cracked 1,200 years ago. This is what you would do if you were 7 years old and just found an amazing encryption scheme. Don't use it. And that goes for anything I'm showing you today, even the stuff that is strong encryption. Don't use it because the implementation matters. And if you make one mistake, you're going to go and think that you are secure, but you're not. So, First World War, 1917, I want to say. The United States was not involved in the First World War yet, even though the German submarines had sunk a passenger liner called the Lusitania This stirred up a lot of emotions, made the Germans promise to restrict their submarine warfare. They would only surface with their submarines before actually shooting at targets. So essentially, look at what you're shooting, which made warfare less effective for German submarines. But Germany was not doing well in the war, and not everyone was a fan of this restricted submarine warfare, and they really, really wanted to resume unrestricted warfare, submarine warfare, but they did really, really not want to drag the US into the war because reasons. You don't want to mess with the US. So this guy, Arthur Zimmermann, the German foreign minister, he cracked a brilliant idea. He was like, what if we speak to the Mexicans who have a grudge with the US over a couple of states that the US took from them? And we promised the Mexicans material and financial support to attack the US in case the US involves itself in the First World War. Smart, right? But he had to communicate that. And the British had, like in the opening days of the wars, they had dug off the undersea water cables. So this information had to be sent over wireless communication. It went via, I think, Stockholm and the German embassy in Washington, D.C., and then on to Mexico City. And so the Germans encrypted this message. And the British, because they are pioneers in decryption cryptography, they intercepted this message. They partially decoded it and found that, hey, this is probably important. So they actually finished decoding the message and found what the plan actually was. And they informed the US government, because we were friends already back then. And in a stroke of genius, because the British didn't want the Germans to know that their message had been cracked, they helped the US decrypt the message sent from the legation in Washington to Mexico, which was worded slightly different, and that message was leaked. So everyone thought it was the Mexicans who leaked the message. That was smart. This was publicized in US newspapers. It was dragged up in Congress. Everyone was really pissed off at the Germans, and so the US got involved in the war. So it backfired because the Germans thought their ciphers were secure. Couple of years later, Second World War, the Germans invented the Enigma machine. This was far, far more advanced. It took a lot of effort to crack this machine. I'm not going to go into all of the details, but it was basically the first block cipher as we know them today, only in a very mechanical form. And the people at Bletchley Park invented the world's first computer to crack it, even though for a long time we thought it was the ENIAC who was the first computer. So computers changed everything because of the massive computing power. You could just run entire messages in milliseconds through a computer and have it encrypted and decrypted. And with that came what we call block ciphers. Now, the first substitution ciphers we looked at, they substitute one character at a time to create the encrypted text, whereas a block cipher consumes blocks of text or bytes, typically 16 bytes or whatever, which again makes it just so much harder to decrypt all this stuff. DES was a standard that came and went. It was really a weak crypto. It was replaced by something called AES, which is the Advanced Encryption Standard. If you buy a USB stick, it probably has some kind of AES encryption built in, as does your SAN host, as does most stuff where there's in-place encryption of one kind or another. This is what a modern block cipher works like. You have a number of so-called substitution boxes, or S boxes for short. These do various things. It could be an XOR, it could be a mathematical operation of one sort or another, and this goes as deep as you want it, so I'm not going to elaborate a lot on this. You put these in sequence, which forms the entire round, and then you do a number of rounds. So if you design this, it's computationally super efficient. You can push a lot of bytes through an encryption algorithm like this in very, very short time. So let's run through AES really, really quickly for those of you who brought your thick glasses. So if you think you have if you look at the plain text at the top, we're going to translate that to hexadecimal code just for to make it practical. And the password will do the same. We'll put the plain text, which just happens to be 16 bytes, in a data frame. This data frame is what we're going to be working with. And if you have more than 16 bytes, there are just going to be more and more and more frames, right? We're going to expand the key according to an algorithm. This creates as many keys as we need. No, not as many keys as we... Depending on the key length, this creates a number of keys that are 16 bytes each. Now, the first round, we're going to XOR the data frame with the first key. XOR means that we split every value into its binary components if one but not the other is 1. So if the top one is 1 but not the bottom one, or vice versa, it results in a 1. Anything else results in a 0. So that's an XOR operation. And the nice part of this is it's reversible, which will help us in a second. You don't need to remember this. I just want you to have seen it to understand what goes on. There's no test. The next step is a substitution box. This is basically the same substitution encryption that we looked at very early, the stuff that was broken 1,200 years ago. But yeah, it's just we exchange values for other values, basically. After that, we shift the rows. So we basically just jumble them around in a predictable manner. And after that, we perform, it's a matrix multiplication. I have no idea what a matrix multiplication does because I never made it to university. You'll just have to trust me on this. And then depending on the key length, we repeat this cycle 9, 11, or 13 times to use up the entire key. That's AES encryption. This is the standard. If you encrypt anything, if you run a BitLocker or whatever, it's AES encryption. It comes built into so many appliances. On a modern PC, you can throughput something like 10 or 15 gigabytes per second of AES encryption. It is super efficient. It takes something like 18 CPU cycles per byte to encrypt, which is astoundingly quick. How are we on time? Thank you. All right, we're doing well. Hashing and encryption. These are basic concepts that I need to separate for you. Who knows the difference between hashing and encryption? Yes, thank you. So, when you're encrypting something, you're generating a ciphertext. The ciphertext is reversible, so you can, using the same key that you encrypted it with, you can go back to the plain text. Hashing does not. Hashing generates a checksum, something that almost uniquely identifies a string of text or a piece of code or whatever. The advantage is also that if you encrypt a megabyte of data, it comes out as about a megabyte of ciphertext. Whereas if you hash a megabyte of data, it comes out as maybe 16 bytes or what, depending on which hashing algorithm. If you've done a git commit, you get the commit number, which is a long hexadecimal string. That's a SHA-256 hash. So it takes your entire commit, all of that data, and it hashes it down to one checksum, which you can then uniquely identify your commit with. So encryption is reversible, hashing is not. Encryption uses a key or password, hashing does not. And the length is the same for encrypted text, but not for hashing, which generates a fixed width. So here's the problem with hashing. If you store passwords in your database, most of us do, right? In one way or another. The industry practice is to hash the password. Now, hashing the password means, because hashing is in theory not reversible, if someone takes your hard drive and walks away with it and puts it in their own laptop and starts investigating your tables, a hash won't give them the actual password unless they've already taken the 10,000 most common passwords in the world and computed their hashes, in which case they will have a simple lookup table to just compare hashes to hashes, right? And those are called rainbow tables. If you're in information security, you know exactly what those things are. The way to fight rainbow tables is to use what we call a salt. You prefix or suffix a specific set of characters, and those characters can be saved in the same table right next to the hash if you want to, as long as you rotate them and always have new hashes for new salts for every password you save. If you salt this password, it comes out as a completely different hash, right? All of a sudden, we've made the password much, much stronger. If you use a different salt, again, it comes out as a completely different hash. So this is called salting. And the right side is actually the industry standard on how to save passwords in a hashed manner so that they are not easily cracked. Again, hashes are used for Git commits, for storing passwords, detecting changes, signatures. Question? The question was, if you're storing the salt next to the hash, how does that not allow you to use a rainbow table? Because your rainbow table won't include the salt characters because the salt characters make it a password. Yeah, so the password becomes 2 or 4 or 8 bytes longer. And if you think about it, just adding, if you have a salt of 4 bytes, that adds 4 billion something and change different permutations for every password. So all of a sudden, those rainbow tables are just unmeasurably big. That answer your question? All right. Now let's get into the real math. So asymmetric encryption solves an important problem for us. This is also called public key encryption. You may have heard of RSA or elliptic curve encryption. I have no idea why it's called ECC and not ECE. I just thought of that now. Here's the problem with symmetric encryption. If I want to exchange secret information with Anthony, for instance, who is very, very far away from me, how am I going to get the key to him? He has to know the key before I send him information. Otherwise, I can't just say, I'm going to use this key, right? So asymmetric encryption using mathematics is a way of solving this problem in what I think is a very, very clever way. And this was invented in the 70s. So the recipient of the message sends a public key, something that can be posted on a home page, basically. The sender uses an encryption function and that public key to generate a ciphertext, which the sender then can send back. And here's the good part. Matching with the public key, the recipient has also generated a private key. So those have a mathematical relationship so that the recipient can use the same function, but instead of the public key, they can use the private key to decrypt this. This is just genius. And it relies on the fact that the reversing of the function is so hard. It's a one-way function within air quotes because it's technically not one way, but it is extremely hard to reverse. But if you have the private key, you just run it forward, right? So you never have to reverse the function. An Australian scientist once put in a book, I think this 1874, I have this huge number, 8 billion and something, and I think it's highly unlikely, which he had calculated with pen and paper. And he said, it's so unlikely that anyone will ever find out which 2 primes you can multiply to make up this number. Oh boy, was he wrong. But what he had discovered was essentially the foundations of RSA encryption. So I'm going to have to do some very, very introductory math for you to keep up with what's coming. The modulo. How many people know what a modulo is? Yes, awesome. So the 10th modulo of a number is if you just cut off the last number. That's the modulo 10 of a number. It's essentially as if you changed number base and just cut off the last number. So if you think of numbers, integers as a scale from left to right, those are the modulos that you see on screen. Clear? Thank you. A prime number is a number that cannot evenly be divided by any other number. So prime numbers are special. And if you think about it, that means every number, every integer, by definition, is either a prime or a factor, i.e. a multiplication of two or more primes. This is going to be important for us later. So here's how RSA works. You make up two prime numbers, large prime numbers. The real RSA numbers are much, much bigger than these. You keep these to yourself. These are your private numbers. If you multiply those by each other, you get an even larger number, which is no longer prime, but the factor of two primes. This is your public key. For reasons I'm not going to get into because I don't have the mathematical chops, we're going to find the least common multiple, i.e. the least common modulo, basically, of p minus 1 and q minus 1, which is, just take it at face value. We're going to move on. Then we're going to make up a number, any number. This is a public number that we can share with our sender. We'll call it E. And using E and P and Q, we can compute another private number. So D is secret. Only we know D. But it has a special mathematical relationship so that it fits in this puzzle. And it's a totient function something something. Again, gloss over. Now, we have a public key, which is E and PQ. And E and PQ, we can go ahead and put in our mail footer. We can post it on our home page. We can publish it in our GitHub repo, wherever you get your keys. The private key goes in the wallet. We'll keep that to ourselves. Now, E and D together can be used to compute all of these private values. So it's super important that you keep your private key to yourself. Suppose we have a plain text. I've converted it to an integer, but this would be as hexadecimal value, which is also an integer. The way we encrypt it is we raise the plain text to the power of E. And you can see how these numbers get really big, really quickly. These numbers become immense in actual real-world applications. And then we take the modulo PQ. So we cut off the last couple of digits, basically, in corresponding to PQ. Everyone with me so far? Awesome. Here's the tasty bit. This is the thing that will bake your noodle. If you take the ciphertext and raise it to the power of D modulo PQ, you get the original text back. You get the original plain text back. So it's the same process, the same mathematical process to encrypt and decrypt using the public key and the private key. And this is fundamental to everything we do in RSA, including things that we'll get to in a second. So the reason this works is because the green arrows are relatively easy to do. Even to the power of a huge number, modulo huge number, those things are relatively easy computationally. They're 4 or 5 lines of code, really. This part is immensely difficult. Like if I gave you a number that is 1,000 digits long and ask you which 2 primes would you multiply to get to this number, you won't be able to do it, I promise, not with all the supercomputers in the world. Here's a number I computed. This is roughly a 4096-bit key. And thing is, we're in 2024, so I had to incorporate some type of AI into this presentation. So what did I do? I asked ChatGPT, like, which 2 prime numbers can be multiplied to form this number, okay? And I really thought I'd bring down a data center because it was very quiet for a minute. And then it said something like, RSA is typically used blah, 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 and it gave me this. Spoiler alert, it's not. You got an F. No, here are the real keys that I used, P and Q. So these are the types of size of values that we're dealing with, and the best current guess, if you used a really, really good supercomputer, it would still take you tens, even hundreds of thousands of years to just brute force this value. That's the current best guess. So if you guessed the P and Q values correctly, don't tell anyone. There's not a government in the world that would not kill you for that information. All right? There's if you're particularly mathematically inclined, there's a competition on RSA's homepage where there are a number of primes. The largest one that's been cracked so far is RSA 250, equivalent of 800 and something bits. It took the equivalent of 2,700 CPU core years. That's a lot of Azure credits to crack that. What we looked at before was a 4096 bit. So every time you add 1 bit, the complexity doubles, right? Not even going to get into elliptic curve because I don't understand this stuff, but this is the other asymmetric encryption algorithm. It's the same principle. It's very easy, I dare say, to compute forward, but very difficult to compute backwards. But it has no place in an introductory session. So how do we use asymmetric encryption? Asymmetric encryption is not at all as fast as AES that we looked at before, but we can use it to just exchange keys between sender and recipient, right? So I can give Anthony my public key, and he will encrypt a session key and send it to me using that public key. And only I have the private key, so only I can decrypt the session key. And now we both know a secret session key, and we can start communicating efficiently. That's effectively what happens every time you go browsing, you check your email, you log into your time reporting or whatever happens, even if you use a TLS when you connect to your database server. That's what happens under the hood. So this is where we are in the big picture, right? We have the client and we have the server. The client sends a random message. The server also sends a random message. We'll get to why that is important, but the sender also sends the public key and says, if you want to talk to me, here's my public key. We'll take it from there. The client then, and the server identifies itself using a certificate, because how else do we know we're actually talking to the server, right? So how do we know a certificate is real and not just a piece of paper where it says, I am the server, promise, like you trust me, bro? And that brings us to signatures. Signatures use the exact same method that we use for encryption, decryption, and RSA. What you do is you make a digest, a hash, of whatever it is the certificate contains, or the actual thing that you want to sign. So if you want to sign a message that you're sending to a coworker, what you do is you hash that message, you get the 16 or 64 or whatever bytes, and then you raise those, you raise that digest, the result of the hash, to the power of D, which is your private key. Only you have that. No one could create this signature unless they had the private key. So that's what the signature proves. The recipient gets the message in plain text and the signature. The recipient can take your signature, raise it to the power of E, which is the public key that you've published, and compare it to the signature that you sent, right? So they can verify your signature that your hash is authentic, essentially, or your signature is authentic, but they couldn't reproduce it themselves. So anything changes in the message, the hash and the signature won't match up anymore. We use this for code signing. If you double-click an application that you downloaded off the internet and it says, publisher unknown, someone hacked together this .exe, are you sure you want to run it? That means it doesn't have a code signing certificate. Or if the certificate gives you a warning and it says, I'm Microsoft, trust me, bro, but the certificate doesn't match up because the signature is all wrong, it's because we signed the entire .exe file, right? Again, hashes are always constant size. We also use it for DNSSEC. We can sign DNS messages so that you know you're talking to a correct DNS record, and for certificates. So, suppose I want to browse to my home page. I contact the server and say, hey, are you strd.co? And the server says, yes, I am. Here's my public key, and here's the certificate to prove that I am me. How do I trust this certificate? How do I know who issued the certificate? Could you just make up a certificate? You could. It would be a self-issued certificate. But in this case, the web server owner has actually gone and made a certificate using a certificate authority, someone who is trusted to issue certificates. So we have a certificate for the certificate authority, the CA, as well. So how do we know the CA is, how do we trust the CA? Well, because the CA has a signed certificate from a root certificate, root CA. A root CA is like any other CA, but we already have a copy of their public key, I suppose, on our computer. If you install a new operating system in Mac OS, Windows, Linux, it comes with a bunch of CAs already installed. These are CAs that we trust, the root certificates. So because we trust the one that we have on our computer, we also trust that strd.co is who they say they are. And then we can start communicating. So this solves the problem of identifying who we're talking to. Otherwise, you could run into man-in-the-middle issues, which we're going to look at. So the certificate chain is basically the person or server you're talking to IDs themselves using a certificate, and you can see on the certificate who issued the certificate, you can see who issued the issuer's certificate, and so on, until you would go all the way back in the trust chain to someone that you actually trust. How are we on time? 18, thank you. So in our big picture, we validate the certificate to make sure the server is actually the server. And I mentioned a man-in-the-middle attack, so I'll just scroll that really quickly. If we contact a server and the server doesn't have a certificate, it just says, here's my public key. How do we know we're talking to a server? We could be talking to an attacker in the middle. So the attacker will obviously say, here's my public key, the attacker's public key. And it all checks out, right? So we can encrypt text, send to the attacker who can decrypt the text, contact the server, and pretend to be us. So this is a man-in-the-middle attack. I think there's a newer name now. We're not supposed to say man-in-the-middle. It's an MITM attack. The way to avoid this is to actually check the certificate that we're connecting to. If you are in the SQL Server space and you're connecting to a server and you get a certificate error and you check trust certificate, guess what happens? The certificate you're getting back is invalid, and SSMS says, it's fine, we're okay. So if we're checking the certificate, the client will see that the certificate doesn't line up with the server we think we're talking to. I'll pass through that. So once we've validated certificate, we'll send what's known as a pre-master secret, which is just a code that the client made up, along with the server random and the client random, to identify that, yes, we're still in this conversation, so that the server knows that we're not talking to the wrong party. We encrypt that with a public key that we got from the server. Both of us now have session keys, and we can speak AES, or symmetrical encryption, to each other using this session key. And this bottom part with the symmetric encryption is highly efficient. This is super, super high performance, whereas if you want to do asymmetric encryption on larger amounts of data, you'd better invest in a more expensive computer. So here are all the moving parts to sum up. A server needs a certificate so that we know who we're talking to. The certificate is hashed and signed with the issuer's private key. That way we know only the issuer has approved that this certificate is genuine. The recipient of the certificate in the public can verify this by also hashing the certificate and verifying that the signature raised to the public key is equals to the signature, the hash that they got. So we can verify this. And you see this pattern, this repeating pattern in RSA. It's always the whatever it is we want to decrypt, encrypt sign raised to the power of the public or private key modulo PQ. And then we can encrypt whatever we're sending, the session key, message raised to the power of the private key, public key, sorry, E, modulo PQ. And then to decrypt the same information, we can take the ciphertext raised to the power of D, which is the private key. So only the recipient can do that, modulo PQ. That's a lot of stuff to keep track of. But I think it sums up pretty much. This is the introduction to just understanding what happens underneath. And if you were yawning, I understand that. I'm jet lagged out of my mind myself, so I've been yawning in sessions that have been really good. If there's one single takeaway from this session, understand what happens when you trust server certificate, right? You're implicitly not checking the certificate. And that might be fine if you're using self-signed certificates or you don't have a CA or whatever in your organization, but just understand what happens when you do that. Also help feed blind dogs, I was going to say, by leaving me feedback. Honestly, PowerPoint says I worked over 100 hours on just the PowerPoint slides. I've done even more research than that. I want your feedback. I want you to tell me how I did, bad or good, because we help feed blind dogs when we do. Any questions? Yeah? So what does it take to become a root CA? Does it involve getting on planes and stuff? I think so. There are not many root CAs in the world. There are a number of dozens, maybe. And there have been instances where companies have lost their right to be a root CA, a revocation, which is kind of upsetting to a lot of security professionals. But they are also corporations and also have regular meat bags who make mistakes. So I don't know the process, but it's not easy. You don't just send like an email to your national governing authority and say, hey, can I be a root CA? It's not just sending in your ID card. These are supremely trusted organizations who have a large responsibility for much of the internet security. Quantum computing. That's one of the slides I took out because I was so short on time when I rehearsed this. Quantum computing is a technology still in the making, and the gist of it, as far as my layman's brain understands, is when we do computing in this room, data stuff, we use ones and zeros. We do one operation at a time, right? So either it evaluates as true or false. A quantum computer depends on an uncertainty principle, where in quantum mechanics, you don't know if something results in this or results in that until you've effectively inspected it. Quantum computers, the way I understand it, can evaluate both solutions at once. And you understand that if you're trying to brute force a key, this gives you a massive performance boost. You can evaluate essentially all the keys at once and see which ones stick. It's not that simple in reality, and the way I've understood it from reading up on this is that quantum is a massive performance boost for key cracking, but it's not the end-all of decryption or brute forcing. Work is in progress with evaluating and building encryption algorithms that are quantum safe or quantum, what do you call it when? There's a level where it's not safe, but it's good enough. Also, these huge keys that we looked at, you can just double them in size. Use an 8,192-bit key or a 16,000-bit key, and it will still take an immense amount of time even for a quantum computer to crack it. But this is highly, highly researched right now. This is where we're going with all this in the next decade or two. But at this point, a quantum computer has less computational power than an Apple iPhone, as far as I know. Probably less than a Commodore 64. So it's in the future. Question? Yes. So the question was, with a man-in-the-middle attack, you could essentially register a website which is opel.com or macrosoft.com or whatever. I don't know how many times I've entered mycoresoft.com into my browser. And yes, you could register that domain, you can get a website, and you can get a perfectly good certificate for that website. That's not something that certificates or encryption can really secure. For myself, the passwords I've stored in my login information that my browser suggests when I enter a site, it won't work for macrosoft.com, but it will work on login.microsoft.com because that's what the browser sees. It gets even more tricky with, you can nowadays use UTF or Unicode characters in domain names, which means you could use Microsoft.com where the I is a Turkish I without the dot, or with a slightly different bullet over the I, or things like that, which makes it, this is one of the new security challenges. So, yeah. So the question was, you can check the name on the certificate. Yes, there are certificates where the company name is actually stated on the certificate. There's a name for it that eludes me right now. These are beginning to be less popular now. The usual way, or there's a free way to get SSL certificates. You can go to CAs like Let's Encrypt, for instance. Or you can spend money to buy certificates on the internet. And the people selling certificates on the internet at quite the price, they offer very expensive certificates where the company name is on. And security researchers have found that the validation process is really not that great. So you could, I think there's a security researcher that managed to get a certificate for something very, very similar to Apple Corporation. So you can't really, these things are going out of fashion. It used to be that browsers had a special green title bar when you used a site where the certificate was signed with a name. They've removed that because even browser manufacturers are thinking this is mostly deprecated and useless. We have time for me, do we? Oh yeah, it's a 15-minute session. Wow, we have endless time for questions. Shoot. So if I understand your question correct, there are a number of root certificates, let's say 50, and what happens if 2 of them certify you, but one of them doesn't? Right, what happens if root CAs are not in agreement? So there's a certification chain, essentially. You have one root CA that certifies a CA, or a chain of CAs that leads to your certificate. It's not a tree. You don't have multiple certifying. Yeah. So, all right. So to summarize, what happens if a root CA is compromised? There are examples of this. There was a Dutch root CA that was compromised a couple of years ago. The attacker managed to issue authentic gmail.com certificates, set up their own man-in-the-middle attack to allegedly eavesdrop on something like 300,000 Iranian Gmail accounts. There are mitigations out there, depending on how technical you want to be. There's one thing called public key pinning, which I think uses DNS to pin your public key so that your browser remembers the last time I visited this site, that was the public key. And if the public key changes, something's up. It's a mitigation, it's not perfect, but the problem you're addressing is very real. Just recently, I think it's in 2019, the Uzbekistan or Turkmenistan, Turkmen government tried to get, they've been trying for years, they tried to make operating systems and browsers install root CAs for their own CA authority, which is, trust me, bro, we're not monitoring your traffic, right? So they're basically trying to firewall off the entire country and do, you would call it a deep packet inspection, I think, where you decrypt all the traffic, look at it, and then you re-encrypt it and send it on. If you have a root CA to certify your firewall, or if users trust your firewall, that would be, it would be essentially transparent on the browser end. And they actually tried to do that, and browser companies would just not do it. So They basically issued a public message to their people that your internet will stop working unless you install this Trust Me Bro certificate. Question? So just repeating what Simon said, he works for a root CA in Sweden, and just becoming a root CA is half the battle. Convincing everyone else that you're legit is like the rest of the fight. How are we on? Yeah? Oh, cool. MD5 is one of many hash algorithms. I believe MD5 is deprecated because it's not secure. And a hash algorithm that is not secured probably means that you can create a hash by forming a message in a certain way. So you can reverse engineer it essentially. If you've signed something, someone can intercept that message, alter the message to mean something else, but alter it in a way so that it generates the same hash, which would make its signature the same. So that's one of the reasons I think MD5 has been deprecated, I think. You're nodding as well, so I'll take your word for it. Yeah. I'm going to wrap it up here. Please just find me anywhere, ask me questions, because I can talk until the sun goes down about cryptography, and probably until sun goes up again. So thank you so much for attending my session. Please leave a review.